So this section is about rates of change in natural and social sciences. So remember that a rate of change, well, a change in an x variable is the difference between x2 and x1. So it's just how far apart are they? That's what your change is. Your change in y is the difference in the function values. Then your average rate of change would be the change in y over the change in x. So it's just basically a slope. That's all it is. Your instantaneous rate of change would be the derivative of y with respect to x. And so that's the limit as delta x goes to 0 of delta y over delta x. And that's what we're going to look at. We're going to be looking at these rate of changes and what's happening in terms of physics examples and social science examples, mostly physics examples. So let's talk about some applications. In physics, this is a problem from the textbook. It says a particle is moving. Have a mistake there, so I'll type it. Moving according to the laws of motion with S equals F of t, t being greater than or equal to 0, where t is measured in seconds and S is in feet. So here's your function. This is the function we happen to have. And what I want to do is look at what this function is going to do. So this is, again, your position function, what's happening with the function. So the first thing we might want to do is find the velocity. So remember, the velocity is just the rate of change in position. So velocity is the derivative of the position. The position function is f of t, so it's just f prime of t. So given that f of t was 0.01 t to the fourth minus 0.04 t squared, t cubed, sorry, then you bring down the power, so bring down the 4, so it'd be 0.04 t cubed, subtract 1 from the power, bring down the power, so it'd be negative 0.12, t cubed becomes t squared. So there is your velocity at time t. What I might want to know is, what is the velocity after 3 seconds? So in that case, I would actually find what the velocity is at 3 seconds. So I put 3 in wherever I see a t. So I had, again, 0.04, 3 to the fourth, minus 0.12, 3 cubed. I'm sorry, I got the wrong numbers there. This is t cubed, and this is t squared. And you go find out what that is, and you find out that is actually 0. And this was in feet, was the position, and time is in seconds. So given that velocity is position over time, it would be feet per second. Okay. The next question might be, when is the particle at rest? So the particle will be at rest when the velocity is 0. So looking for when the velocity is 0, that would be 0.04 t cubed minus 0.12 t squared, and you're going to set that equal to 0. And you just have to solve this equation. So the first thing you do is factor out a t squared, because you see a t squared in both terms. And then you see, oh, t equals 0 for this one, and this one you solve and find t equals 3. And these are both in seconds, so don't forget your units. So the particle is at rest at 0 and at 3 seconds. Then the question might be, well, when are we moving in the positive direction? And so we want to know, when is the velocity positive? So again, we take our velocity equation, and we happen to know that our velocity equation is 0 at 0 and at 3. So we want to know when the velocity is positive, because we want to move in the positive direction. So we want to know when the velocity is positive. So pick values less than 0, put into your velocity equation, see if you get a positive or a negative number. You will get a negative number if you pick a number less than 0. Pick a number between 0 and 3, like 1, put that into your velocity equation. Again, you'll get a negative number. Pick a number greater than 3, like 4, put it in, and you get a positive number. So we know that you're going to be having a you're going to have a positive direction when t is greater than 3, greater than or equal to, actually just greater than 3 seconds. Or you can write this as 3 to infinity like that. Okay. So now we'd like to know the total distance traveled. The total distance traveled because of in the first 8 seconds it is. Since what we just did, we know that we're moving in the positive direction when we're between 0 and between greater than 3 seconds. But between 0 seconds and 3 seconds, and we don't worry about less than 0 because we're saying time starts at 0 and we want the first 3 seconds, we know that we're moving in the negative direction. So in that case, if I found f of 3, subtracted f of 0, that number would be negative. But I want total distance, not displacement, but total distance, so I want that to be positive. Then I'm going to look at the velocity, the function at 8 seconds minus velocity, the function at 3 seconds, the position at 3 seconds. And again, I want that to be positive. It will be because we were moving in the positive direction. So I don't need the absolute value bars, but I went ahead and did it just for completeness. And I find out my total distance traveled is 21.2 feet. Okay. And what I want to do is I want to kind of talk about what this object is doing and how is it moving. So I'm going to think about this as here's my axis. And we're going to start at t equals 0. And then we're going to go to t equals 3 seconds. And from 0 seconds to 3 seconds, we're moving in the negative direction. So this is the negative direction. At this point, we now turn and start moving in the positive direction from 3 on up to 8 or on up. So we can now actually talk about what direction we're traveling. So this is when position is 0. This is when your position is actually negative 0.27. And then you're going to come back and go the other direction. Okay. Let's say I want to find the acceleration at time t. So my acceleration would be, again, the derivative of velocity. So my acceleration is the derivative of velocity. It also happens to be the second derivative of position. My velocity equation was 0.04 t cubed, sorry, minus 1.2 t squared. So that would be 0.12 t squared, because the derivative of 0.04 t cubed, bring the power down, subtract 1 from the power, and then minus 0.12 times 2, or 0.24 t. Again, bring the power down, multiply by the 0.12, and subtract 1 from the power. So there's my acceleration function. I also would like to find the acceleration after 3 seconds. So now I just take that function I just came up with and plug 3 in for it. And I come with 0.36 meters per second squared. Okay. I'd like to now graph the position, velocity, and acceleration functions for 0 to 8 seconds. I'm going to go ahead and use Desmos. So I'm going to go bring up Desmos. So I've got my position function, which is y is equal to 0.04, I'm sorry, 0.01 t to the fourth. I'm going to use not t, but I'm going to use x, minus 0.04 t cubed. And I can't use t, I got to use x, sorry. So there's my position function. My acceleration, my velocity function was 0.04. We'll call this y1. 0.04 x cubed minus 0.12 x squared. And then my, call it y2, my acceleration we just came up with was 0.12 x squared, and then minus 0.24 x. So there's all of them. That's what they look like. That's what the shapes are. And you can see what's happening. Sometimes my acceleration is negative. Sometimes my velocity is negative. Sometimes my position is always, it's negative because we're going backwards. So we have all those values in there. And I'm going to go ahead and take a picture of this and put this in my notes. So I have this. You know what? I'm going to redo this just ever so slightly because I wanted to go all the way to 8 seconds. And I noticed that my Y doesn't go all the way up there. So we'll make this up to 20. And I'm only going to go from 0 to 8 seconds, so we can just do it from there. I'll go to 9 seconds just to make sure I see it all. All right, so now I get a little bit better graph. And 20 seems to be a little high because I don't see a lot of detail at the bottom. So we'll make that maybe 15. And maybe even 10. Let's see if 10 works. Nope, we're going to have to go to 15. Oh, no, not even 15 works. So we'll have to go to 20, back to 20. Oh, but we don't need to go down here to negatives. We'll go down maybe -2. That gives us a little bit better picture. All right, so now I can go ahead and snip it. I'm going to put this in my notes. All right. Make this just a little bit smaller so I can see a little bit better. Okay, so there's my graph of my position, acceleration, and so forth. All right. We're going to use that to help us with a few more things here. All right, we want to know when the object particle is speeding up and when is it slowing down. So the main thing about this is that an object, if its velocity is negative, it just means that it could be going to the right. It could be slowing down. It could be going to the left. So what we need to figure out is exactly what is it doing. And it turns out that an object is speeding up. Let me actually type this. When the velocity is positive and the acceleration is positive, or the velocity is negative and the acceleration is negative, because that means that my velocity is in the same direction as my acceleration. So my object will be speeding up. It is slowing down when the velocity is positive and the acceleration is negative, or the velocity is negative and the acceleration is positive. Because what that means is that my object is, if my velocity is positive, my acceleration is negative, then it's pushing against it and it's actually slowing it down. If my velocity is negative, that just means it's going that way, and my acceleration is pushing against it because it's positive, and again, it would be slowing down. And they don't technically push against each other, but that's kind of a way to think of it. So what I need to do is figure out when this is going to be. And so I already know when my acceleration, my velocity is positive and negative. Remember, we found out for the velocity that the velocity was negative if we're less than 0, which we're going to ignore, negative if we're between 0 and 3, and positive if we're bigger than 3. I can do the exact same thing with the acceleration. So I need to remember that my acceleration function was equal to, my acceleration function was equal to 0.12 t squared minus 0.24 t. So again, I'm going to factor out a t. I get 0.12 t minus 0.24. I want to know when that's 0, because we have to figure out where the zeros are, and then from there we can figure out where we're positive and negative. So t equals 0 is one of the zeros, and t equals 2 is the other 0. So we now have these two places, and again, I'm going to create an axis here. This is my acceleration axis. If we're less than 0, then t is negative. And let's say we have -1 here, this would also be negative, and a negative is positive. Again, we don't care about less than 0 because we're considering time starting at 0. If we're between 0 and 2, then the time is positive, and this one is negative. So we have a negative times a positive is negative. If we're bigger than 2, t is positive, and this term also will be positive. A positive times a positive is positive. So I now know my acceleration is positive from 2 to infinity and negative from 0 to 2. So now we can figure out when are we speeding up. All right, so when I look at this, I can see right now that my velocity is positive from 3 on. My acceleration is positive from 2 on. So therefore, they're going to be the same sign from 3 on. So we're going to be speeding up from 3 to infinity. But let's see if there's somewhere else where they're going to be speeding up. So from 0 to 2, my acceleration is negative. From 0 to 3, my velocity is negative. So from 0 to 2, they're both negative. So we're also speeding up from 0 to 2. We're slowing down when they're opposite signs. So they're opposite signs from 2 to 3. So we're going to be slowing down just from 2 to 3. And that's what we can do with physics-wise. There are other applications for physics also. There's a current application where you can talk about the average current, which is the change in charge over time, Q being charge. Current is the capital I is what we use. Electrical engineers use a small I. I like capital I. And the limit as delta t goes to 0 is delta Q over delta t. So the derivative of Q over time. So current is just a change in current over time, the derivative of current over time. We also have linear density. This is how much, what is the linear density of an object? And we look at the mass. Your function is how much mass you have, and you also have an x. So from x1 to x2, you're going to have a change in mass, and you're going to have a change in the distance you're traveling. So your function is your mass, and you're going to look at that change in mass, and that's your average density. Your density, rho is the symbol for density that is used most of the time. And it'll be the limit as delta x goes to 0 of delta m over delta x, or the derivative of mass over x. We're going to show some more applications in another video, but this is just an introduction to some of the physics applications.